want to look at the Gibbs energy change for a phase transition in a little bit different way in this video. And what I want to do is to track how the Gibbs energy changes as we change the number of moles that are in one phase versus another. So for example, I may have a liquid on one side here and a vapor on the other side. And I start off with N sub L moles of the liquid. I start off with N sub V moles of the vapor. And what I'm interested in is if I take some small amount of moles, I'll call that little dn, and I move them from the liquid phase to the vapor phase, how does that change the Gibbs energy? Now, part of what I need to realize here is that my total Gibbs energy for this system is going to have two components. It's going to have one component that's due to the Gibbs energy of the liquid and another component that's due to the Gibbs energy of the vapor. And I don't want to necessarily assume that those are the same. And in fact, at many temperatures, those are very different. And in fact, we want to make sure that we're accounting for the phase of our substance as well as other things like the temperature, the pressure, and so forth. All right, so these things may end up being different going from this. So then what I'm really talking about is a Gibbs energy for the liquid that starts off at N sub L moles, but it loses a little bit to become N sub L minus dN moles of this liquid. And the Gibbs energy of the vapor would have the opposite change. It would start off with N sub V moles, but it would add dN moles to that. So somehow I want to relate these things to incremental changes in the Gibbs energy itself. So in other words, what I may want to do is take this and sort of cast it as a incremental change in the liquid part of the Gibbs energy, and that would be equal to the partial of the liquid part of the Gibbs energy with respect to the number of moles that it has in the liquid times dN. And since this is a negative here, I'll put a negative sign out in front just to keep us honest. For the vapor phase, I'll have a very similar sort of expression that I would write this as the partial of the Gibbs energy of the vapor with respect to its number of moles times dN. Now, I know that Gibbs energy is in fact a function of temperature and pressure ordinarily, but I also know that it is an extensive property. So in other words, I really know that Gibbs energy can be written as N times the molar Gibbs energy. So I know that there is inherently a dependence of the Gibbs energy on the number of moles. So that reassures me that in fact these changes in the Gibbs energy that I'm writing here are something that I might be able to track if I do my mathematics and do my accounting carefully. Now, what will this give me in the end? I want to find the change in the Gibbs energy for the whole system. And it's going to have a liquid component and a vapor component. So I can write this as dg liquid plus dg vapor. But I can now substitute these things in. They both are multiplying this same increment because any moles that are lost by the liquid are gained by the vapor. So I can actually write this out like this. I can write dg vapor with respect to the number of moles of the vapor, and I can subtract the liquid with respect to the number of moles of the liquid, and then these things multiply by dN. Now, I started to say something earlier and didn't finish it. I know that Gibbs energy is a function of temperature and pressure, so in fact I need to include those as being held constant when I take this derivative down here and these derivatives here. So I want to be sure to include that so that I'm not leaving anything out. All right, well, these things down here might ordinarily be something difficult to determine, but since we know that the Gibbs energy is an extensive property, they're actually not too difficult at all. In fact, I could write that, in fact, the change in the Gibbs energy of the vapor with respect to its number of moles at constant temperature and pressure is really just going to be the molar Gibbs energy of the vapor. But I'm going to give this molar Gibbs energy of the vapor a different symbol. I'm going to call it mu. And we'll talk about that in just a second. So it also means that I can do the same thing for the Gibbs energy of the liquid when I take its derivative with respect to its number of moles at constant temperature and pressure, then I'm going to set that equal to the molar Gibbs energy of the liquid, which will be equal to its mu sub liquid. Now these two things that I've introduced here, these mu factors, are something we call the chemical potential. So mu is the chemical potential of this system. Actually, it's the chemical potential individually of the liquid and of the vapor. Now, you might say, well, why did you not just use the molar Gibbs energy? That's a perfectly good way to do this, and I agree with you. It is a perfectly good way to do it. Historically, however, we have introduced this notation of considering the chemical potential as something separate. And I think one reason for this is that this is a very handy tool to use when we have a system whose components are changing. If we have just a one component system and it might have a different temperature and pressure but nothing else is happening, then we don't need to worry about all of this stuff. But as soon as we have different kinds or separable kinds of a system, types of a system, that transform into one another, then we need to track that somehow, and this chemical potential gives us a means for doing that. Now, I want to note then that we can write this change in a differential change in the Gibbs energy now using this expression, because I'll just factor in mu vapor here and mu liquid here. I can write this as simply mu vapor minus mu liquid times dN. And this is a perfectly good expression for what's going on in this phase transition. Now, I also will note, though, that at a phase equilibrium, we know that the change in the total Gibbs energy has got to be zero. Now, what does that mean for this equation? Well, I know that dN is not equal to zero. Why? We have a dynamic equilibrium at work here, which means that constantly we've got moles of liquid becoming moles of vapor and vice versa. We also could have a phase equilibrium at which one is being in the process of being converted into the other, in which case I am making a tangible change, but I'm not changing the Gibbs energy at all of this process. What this means, I guess the bottom line, is that when we do this, it means that the chemical potential of the vapor and the chemical potential of the liquid are equal to one another at a phase equilibrium. And in fact, this is going to be generally true when we're at an equilibrium that is denoted by G equal to 0 or delta G equal to 0. We will find that the chemical potentials of things will be equal to one another at that equilibrium point, and that's part of what defines this equilibrium. Now, I want to finish one last thing, and that is to say we define these chemical potentials in terms of the molar Gibbs energy, but we also know that the total Gibbs energy is equal to the number of moles times the Gibbs energy. So what that tells us, in a sense, is that the Gibbs energy as a function of temperature and pressure, we should probably also include number of moles, can be set equal to the Gibbs energy, the molar Gibbs energy as a function of temperature and pressure times the number of moles, or it is the chemical potential times the number of moles. And I'm going to write the chemical potential now explicitly as a function of temperature and volume times the number of moles. And now you'll see that all of these equations will in fact be satisfied by these differential relationships, or they do satisfy those differential relationships. But moreover, if I have more than one component in a Gibbs energy, so if I have Gibbs energy of two components, I can actually write that as the chemical potential of one component times the number of moles of that component plus the chemical potential of another component times the moles of that component. And it's this function, it's this equation that really gives us some power in how we deal with the Gibbs energy. I've actually gotten way ahead of myself. This is stuff we're going to talk about more comprehensively in the next module, but I think it's useful to know this and to see how some of the things that we do with phase transitions will have an impact on our later studies about mixtures.